continuing on with hyper-Rayleigh scattering, an important question to ask and answer is, what is the analytical utility of the method? In other words, how do we take the hyper-Rayleigh scattering set of intensities and relate those back to molecular symmetry and symmetry and structure? And we only have a small number of observables. And so how do we connect those experimental observables back to molecular symmetry? Before we get into the more general case, let's consider a simple one-dimensional rod-like chromophore. And just to highlight this, if we have a molecule that is dominated by all the interactions along a single plane, such that it only has a rod-like nonlinear hyperpolarizability dominated by beta ZZZ, what do we expect to get for the intensity of the X polarized, the Y polarized, and the Z polarized, which can be measured on either of these in either of these geometries? Well, how do those intensities? What do we expect for the relative intensities of these different polarization-dependent components in hyper-Rayleigh scattering under these conditions?
How does chi-ZZZ relate back to some sort of molecular properties? Because that's ultimately what we're after, right? If we're doing a hyper-Rayleigh scattering measurement, we're not doing it because we want to know the orientation distribution. We already know that. We're doing it because we want to learn something about the molecular properties. So how does this measurement kick back to that? And the answer is through orientational averages. So we know, for example, that IZ, if we're coming in with Z-polarized light, then this would correspond to the co-parallel detection channel, is related to the molecular nonlinear response through orientational averages. And we're going to consider it as an initial test case a one-dimensional rod-like chromophore. If it's a 1D rod-like chromophore, then everything interesting happens along the Z prime coordinate inside that molecule, and beta ZZZ is the only interesting non-zero tensor element. So, as a result, this one's an easy one to calculate. So if I want to know what does chi-ZZZ in the laboratory frame, how does that relate back to beta ZZZ in the molecular frame? In hyper-Rayleigh scattering, because it is an incoherent detection technique, we integrate over all 6 of these rotation operations, not just 3 of them, like we would with this coherent second harmonic generation. So as a result, we end up with, if you do the integration, you end up with a total value of 1/7. Yes, 1/7 of the relative to the total maximum that could be achieved for a delta function orientation distribution. All right, that is co-parallel. So it's reduced relative to a completely aligned system, but reduced by a factor of 7. Let's now look at cross-polarized. If we do the cross-polarized detection and ask how does that compare? If I have a rod-like chromophore, what is my anticipated signal to noise for cross-polarized detection? It turns out, just plug and chug, do the orientational averages, evaluate them over all 3 Euler angles, and you get 1/35th, which is, of course, 1/5 of 1/7. So there's a 5-to-1 relationship between coparallel versus cross-polarized in the limit of this simple one-dimensional rod-like chromophore. Now we can then rotate our detection arm to detection of the polarization induced along the optical axis. And it turns out that we don't end up with 0. We end up with 1/105th, which is significantly less than that 1/7. What is that, 1/15? It's 15-fold lower. But it still is non-zero and predictable based on this architecture, given the assumption of a simple one-dimensional rod-like chromophore. All right, and this is just summarizes those outputs. So if we were to measure the coparallel, then that would give, and compare that to the cross-polarized, if we have Z-polarized light coming in, then that will give us a ratio of 5-to-1. In the sense that the coparallel polarization component is anticipated to be 5 times larger than the cross-polarized for a rod-like chromophore, individual chromophore. Now we can also compare those with, it's a little trickier because now we have separate detectors, and so we have to make sure they're carefully calibrated. But if we were to make measurements at 90 degrees relative to the transmission direction, then in that case we'd expect a 15-to-1 ratio between the transmitted Z-polarized component and the X-polarized component of the 90-degree scattering field. All right, so that's the basic framework for describing coherent all right, so that's a simple, relatively simple one. All right, so that's the one-dimensional rod-like system. Let's kick it up a notch and actually move to a completely general system where we have full, all 27 tensor elements potentially non-zero valued. And then we can use symmetry and simplification to reduce that. But let's build the general architecture next.